Describe and configure an IPv6 address. In this nugget, we're going to demystify the makeup of an IPv6 address to the point where you'll be comfortable enough to not only understand it, but also to configure one. Let's begin. Our objective in this nugget together is to build a rock-solid foundation that we can build on as we enjoy this series together. And to do that, I'd like to start off by taking a look at the purpose of IP. I mean, why do we even have IP? What's the primary function of it? And I'd like to draw your attention to this guy with the jeans on. What is he doing? What is he doing? Well, Keith, it looks like he's reading a map. And I would agree with you. Looks like a map. And what good is a map? A map has amazing information about how the streets are all connected together. For example, if this guy wanted to go from point A to point B, he could use a map to determine the path to get from point A to point B. Assuming the map's written on this side and he's not looking at it backwards. But assuming he reads it correctly, he could get from point A to point B. Well, in a computer network, we have the same concept of street names. However, we don't use names like First Street or Elm Street. We use street names like 10.1.0.0/24. And this is a dotted decimal IPv4 address. So that's 10.10 network. Maybe we have 10.2.0.0/24. And my question is, what exactly is the intersections of these streets? So maybe I have 40 PCs here. I've got 50 PCs here. What is the intersection that brings those streets together? Now, if you're screaming out saying, Keith, the intersection of two different streets is a hockey puck with an R on it, you'd be absolutely right. So we are on the same sheet of music. The router is the intersection between our networks. That's true for a little network at a home office. It's true for the internet, which is a collection of hundreds of thousands of routes. I have learned that if I take something I understand and apply that knowledge to something new, I can carry a lot of it forward. So in that light, let's take a look at this output right here off of my Windows computer. It says that my IP address for IP version 4 is 192.168.1.33. Well, that's fantastic. Yes, it is. But what really is inside that IP address? Inside of that IP address is two distinct components. I've got a network piece, like a street name, and I've got a host number, like a house number. How do I divide that up? Well, the answer is, Keith, you do this. You get out a pen and you put a line right there between the 192.168.1 and the 33. That means everything to the left is the network address, like the street name, and everything to the right is the actual host. And how did I know? How did I know that was the dividing line? And the answer is, it's the mask. So I am going to call upon some of your basic IP version 4 knowledge, that the mask identifies how many bits from left to right are being used for the network. In this case, it says the first 8 bits are all the net, the next set of 8 bits are all net, and the third set of bits are all net, which leaves the last 8 bits available for host addressing. So the line in the sand that divides the network portion from the host portion is the mask. We use a format to represent these addresses in decimal. It's called dotted decimal. We have a decimal number with a period, another decimal number, a period, another decimal number, a period, and a final decimal number. And why do we use decimal anyway? Well, somebody came up with a brilliant idea that, hey, most humans have 10 digits, the thumbs and fingers. So why don't we have a numbering system that goes 0 through 9, 10 different numbers. And then once we get past 9, we'll go to 10, we'll carry the 1 and start over again. So 12, ... we get to 19, we carry the 1 again, 20, 21, etc. And decimal seems natural to most people because we use it all the time. However, this IP address that we have right here in IP version 4, it's really a binary number, like a light switch with all ones and zeros. And it happens to be 32 bits. And so the way that we represent that is we have 8 bits, separated by a period, 8 more bits, period, 8 bits, period, 8 bits, period. So although we see a number like 192.168.1.33, the computer behind the scenes is actually taking a look at the binary representation of those numbers. And the conversion from decimal into binary, it could be easy if you were born doing it. But for most humans, it's not a simple task. It has to be learned. But behind the scenes, that's what's really happening. So Keith, why are you telling me all about IP version 4? I get that it has two parts of the address. It has the network portion on the left, has the host ID on the right, and the mask is used to separate the two. So that draws the dividing line, which part's the network and which part's the host. An IPv6 address has two parts. It's got the network portion on the left, and there's a dividing line, and it's got a host portion on the right, just like IP version 4. Now, the big difference is what? Well, Keith, in IP version 4, we used a mask to indicate how many bits. So this mask right here of 24 bits also is represented like that many times. So this mask of 24 and this mask in dotted decimal represent the same thing. Well, in IPv6, we also use the slash. So if we wanted our mask to be 64 bits or 80 bits or 32 bits or something else, we simply say slash and simply specify the mask right here. So Keith, wait a second. Let me make sure I have this straight. You're saying that an IPv6 address has two parts. It's got the network portion on the left, the host portion on the right, and the mask going from left to right identifies how many bits are being used for network, and whatever's left over is being used for host. Yes, that's it. That's exactly it. Piece of cake. We're done for the day. Well, there's a couple other little things that you really ought to know, and that is IPv6 doesn't use 32 bits. It's not enough. What it does use is it uses 128 bits. So these IP addresses are now a lot longer. In fact, let me introduce you to a binary representation of an IPv6 address. Take a deep breath. So here it is in binary, an IP version 6 address. Now you might be thinking, well, Keith, is this the shortcut? No, this is the long way. I wanted to show you what it really is going on behind the scenes, and then we'll take a look at the shortcuts and how we actually represent this. This is in binary. It's 128 bits long from here all the way to there. And we also know that this entire string of 128 bits represents an IPv6 address. That's true, but it also represents two individual parts. On the left somewhere is the network, and on the right somewhere is the actual host. In IPv6, they like to call it a host ID. You can call it a host address. You can call it a host ID. We're talking about the same thing. And my question for you is right now, how do we know where the dividing line is between the network bits and the host bits in this beautiful IPv6 address? And if you're saying, well, Keith, in the previous discussion, we said it was the mask. And that is exactly right. So if we have a mask, so we said the mask is /64, we would count 64 bits in, which is somewhere possibly right there. Assuming this is 64 and assuming that is really 64 bits over from the left, that would mean everything to the left of this line is the network, and everything to the right of this line is the actual host or host ID. Now, does this mean we're going to have to input these IP addresses in binary? And the answer is no. It would be too time consuming. There would be too many errors. We are going to represent these binary numbers with a different numbering system. In IPv4, we had an address like 192.168.1.32, for example. And those are grouped together. For example, we have 8 bits here, we have 8 bits here, 8 bits represented here, and 8 bits here, and we have a period separating them. That's why they call it dotted decimal. They're decimal numbers representing 8 bits at a time, and the period shows us where one number stops and the other number starts. Well, how do we apply that same kind of concept of grouping our bits inside of IPv6? And the answer is, what they decided to do was take 16 bits at a time. So with IP version 4, it was 8 bits at a time. In IPv6, it's 16 bits. So we take these first 16 bits, we can separate those. Instead of using a period, they now use a colon. So it's going to be 16 bits, a colon, and then 16 more bits, and a colon. And let me finish off all these colons for us. So each one of these represents 16 bits. And then, of course, there'd be a slash, for example, 64 that says, okay, the first 64 bits up to this line are the network based on the mask, and the last 64 bits, because that's how many are left, and they're not being used for network addressing, are going to be for host addressing, or the host ID. So what have we learned so far? Well, we've identified that an IPv6 address is how long? Good, it's 128 bits long. Now we've just learned that this 128-bit IPv6 address is organized into chunks of how much? Good, 16-bit chunks. And how many of those? Go ahead and count those if you would. Get your finger out, point, and let's count how many chunks are there. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 groupings of 16 bits each. And if we do 8 times 16, hopefully that's going to work out to be 128 bits, because exactly that's how many bits are in an IPv6 address. So let's summarize. Number one, we understand that the purpose of the Internet Protocol, or IP, is for logical addressing, street names with routers being the intersection of those. That's true with IP version 4 and IP version 6. The IPv6 address has two parts, very similar to an IPv4 address. It has a network portion on the left, it has a host portion on the right. The dividing line is due to the mask. Where the mask stops, that's the dividing line between the network bits on the left of that mask stopping point and the host bits on the right. For an IPv6 address, it's 128 bits long. It has 8 groupings of 16 bits each, and we've also come to the realization that there's no possible way that we're going to manually input all these ones and zeros. That, my friend, is absolutely accurate. Let's take a look at how we will represent those groups of 16 bits 4 at a time. I've placed up here our 128-bit binary implement version of the IPv6 address for our reference. It kind of reminds me of like one of those microline prints on a check where you have to get a magnifying glass to see it. I am so glad that you and I don't have to put in numbers like that in binary. That would take a lot of time. To input and work with IPv6 addresses, we are going to use something called hexadecimal. And hexadecimal is just a different numbering system. It's not that weird, it's just different. Let's take a look at decimal for a moment. Decimal, how that works is we have 10 digits on our fingers, and we use the decimal numbering system as a human race primarily because we have those 10 digits. It goes something like this. 0, in fact, we can count them out here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh no, we're out of digits. 0 through 9, that's 10 different digits. What do we do next? We carry the 1 right there, and we start over. And once we get to 19, you carry the 1, is 20, and you start over. That's how decimal works, a base 10 numbering system. Binary, which a lot of us had to learn when we worked with IP subnetting with IP version 4. With binary, it only has 2 possible numbers. It's got 0 and 1. That's it. So you start at 0, then you go to 1, and then you carry the 1 and continue. That's all we're doing. So that's a 2, that's a 3, then you carry the 1 again, and that's a 4, and you continue down the line. So binary is a lot of fun, and that's because in binary the positions are 8, 4, 2, and 1. So position A, B, C, and D, that's the weighted values of those. So if we have like this down here, that'd be 8 plus 4 plus 2 plus 1, which is a total of our decimal, 15. Well, we're not going to use binary, and we're not going to use decimal. We're going to use hexadecimal, and let me show you how simple this is. Oh my gosh. When I first learned about hexadecimal, I thought, wow, seems like a pain. However, with this case, with IP addressing with IPv6, it's super easy. Check this out. With hexadecimal, we start at 0, which is a constant. Decimal, hex, binary, we all start at 0. Then we start counting. 1, 2, count with me. If you're in a queue and other people are watching, who cares? Count with me. 3, 4, 5, 6, 7, 8, 9. But check this out. In hexadecimal, it's base 16. They have numbers of 0 through 15. So in hexadecimal, they represent what we would call a 10. In decimal, they use the letter A. So what does A mean? Well, in hexadecimal, it's reflective of a 10 in decimal. And then they go to B and C and D and E and F, and that's when they stop, because it's a base 16. They only have 0 through 15 they can use. So what do when they need to go to the next number? How do you get to 16? Check this out. What they would do for 16 is they would carry the 1, and they would go to this. So what looks like a 10 to us means there's a 16 and a 0, and that's a value of 16. And then this 11 would be 17, 18, 19. But we don't have to even worry about that. The stuff beyond F, you don't have to worry about, because check this out. In an IP version 6 address, we are going to treat every 4 bits on its own power. Which means simply this: if we want to convert these numbers, and I have them down here so they're bigger, but if you look at 0010, that's this guy right here, and the next one 0000 is this one right here. You take each of those 4 bits on their own, and you simply convert them to hex. That's it. 4 bits. So wait a sec, Keith, all you're saying is I need to be able to know the binary and the hexadecimal for 0 through 15, and I'm set for any conversion that I want to do with the IPv6 address. And that's absolutely right. Part of your homework assignment, which I'm asking you to do right now, before you go on to another video, I want you to write out this table. And I'd like you to do it by hand with a real pen or pencil and real paper of some type, a napkin. I would like you to write out decimals 0 through 15. This is the easiest one because that's our native numbering system. I'd like you to write out the equivalent for the hexadecimal because that'll give you a really strong correlation of the values of each of those. And then I'd like you to write out the binary. There's only 16 combinations, 0 through 1111. And I'd like you to write those out. Now, why is that? It's because if you can write out this table, which does take a little bit of practice if you haven't done it in a while, you can then convert from binary to hex or hex to binary, doing 4 bits at a time. Let's do this together. Here we have the first 16 bits, the first grouping, if you will, of that beautiful IPv6 address. So forget the world for a second, just focus on these first 4 bits. Now, in technical school, back in the 80s, I learned that the 4 bits were called a nibble. No kidding. Not a lot of people use that term anymore, but if I refer in the series to nibble, you're talking about 4 bits, and a byte, of course, would be 8 bits. So you take 4 bits, and you say, okay, what's the value of those 4 bits? And you could say, well, if you drew your chart out, you could say 0010, that's right here, and that's a 2. So guess what? A 2 goes right there for your hex. So every character inside of an IPv6 address represents 4 bits. So if we're representing 16 bits right here, what we're going to see in the config is we're going to see 4 numbers. In fact, 2001 represents those 16 bits. So let's do the next one. So 4 zeros. Well, 4 zeros is a 0, so that'd be a 0 in hex. The next set is 4 more zeros. That's the second 0 in the 2001. And the last one is 0001. And that represents a 1 in hex, and that would be a 1 there. So this number is 2001. Let's take a look at the second group of 16, which is right here. So we have the binary, that'd be this group right here of 16 bits. And the first set is all zeros. So you think, well, 0000 in binary equals a 0 in hex, so the first character is a 0. And then we have 1101. Okay, now, If you didn't have this chart out and you wanted to figure out what 1101 is, you could say, well, 1101, that's an 8, a 4, a 2, and a 1. And you add the values that are on. So we have 1, 1, no 2s. We have 1, 4, and we have 1, 8. So that's 8, 9, 10, 11, 12, 13. So you could say, okay, it's 13 in decimal, which is a D in hexadecimal. And that, my friends, is why this number here, the 1101, is a D. And then we have 1011, which is a B, which must be 11. And then we have this guy, which is 8, and that's 8. So all the numbers of 9 and below from hex and decimal have the same value. It's when you go beyond 9 that the hexadecimal characters start going to A, B, C, D, E, and F. The part I really want you to take home from this is the fact that each of these grouping of 4 bits is going to be represented by a single character in hex. And this is the conversion tool right here. Once you start working with it, just realize there's only 4 bits at a time. You don't need to worry about converting 32 or 64 bits or 128 bits. It's just 4 bits, 1 nibble at a time with 1 hex character representing the 4 bits in the IP address. So here we have an IPv6 address that is the same one as up here. So of course, the one at the top is tedious, it's in binary. This one down here is a lot easier. What I think we should do is let's go ahead and configure this IPv6 address on an interface. On the iOS, which I'm going to use as an example for configuring this IPv6 address, I want to point out that you'd never want to do any changes to a production environment that might impact business. That's generally frowned upon. So I'm going to give you some homework assignment here in a moment, but let me go ahead and walk you through setting this up first. From R1, let's go ahead into configuration mode, and I'm going to create a loopback interface that's not currently being used for anything. And then I'm going to assign an IPv6 address to it. So I have logging synchronous on, so it's updating my screen in the event of those console messages coming up. So here's what I've done. I'll press enter, and here's what I've done so far. I've said I want to create a brand new loopback interface, which is not going to harm anything, and I want to assign an IPv6 address to that interface. So the biggest difference with most commands inside of IPv6 as opposed to IP version 4 is we add the keyword IPv6. So if you're thinking, I know how to do this on a router with IP. How do I do it with IPv6? Think to yourself, oh yeah, add IPv6, use the question mark for context sensitive help, and you're off to the races. So this says, I want to add the IPv6 address of this to that interface, and the /64 right here specifies the length of the mask, which means right up to here. So this is the network portion, and this is the host portion. Your assignment, should you choose to accept it, is now two things. Number one is to write out that table with the hexadecimal to binary to decimal conversion. And secondly, I would like you to configure this IP address on a device. Now, you might be saying, well, Keith, I don't have access to a non-production router at the moment. Great. Don't worry about the production router. You don't want to mess with anything in production. But you could do this, the equivalent implementation, you could do it on Windows. You could do it on Linux. You could do it on Junos. You could do it on Cisco. It doesn't have to be a specific device as long as it supports IPv6. So let me clear the screen and have you make sure that you've got this IP address right here and that you're going to configure it on an interface. I'll tell you what's going to happen. For many of you, you haven't configured a whole bunch of IPv6. And what happens to me, this is how I know, is if I haven't worked with it in a few weeks or a few months, I will start accidentally putting in periods, and the operating system is not going to be happy about that. So that's 16 bits a colon, 16 bits a colon, 16 bits a colon, all the way through. Now, the next piece of this journey together is let's take a look at some shortcuts. Now, shortcuts are handy, and here's how the shortcuts work inside of IPv6. In IPv6, if you have a leading 0, you don't have to put it there. So you could say 2001 colon DB8. And because the colons say, hey, that's 16 bits, it assumes that that high order 4 bits, that they're zeros. So you can drop off any leading zeros. The other trick that we can do is that if you have groups of all zeros like this right here, you could represent those with a colon, colon, just like that. So we could have DB8, 0, okay, drop off the leading zeros, 1, 2, 3, 4, colon, colon, drop off those leading zeros, 5, 2, 1. So that would be our shortcut for that. So 2001, DB8, leaving off that leading 0. And now here, some people said, well, Keith, if you can put 2 colons to represent groups of consecutive zeros, how come you didn't do colon, colon here? Because if I did this here and that there, the operating system would not know how many groups of zeros were at each place. See, here's how it works. The system knows there's 8 groups of 16 bits. So if I use a colon, colon, like right here, it says there's 1, 2, 3, 4, 5, 6. Okay, inside of that grouping of the colon, colon, there must be 2 of them right there to make the total of 8. If I did it twice, if I did it here and here, it doesn't know, oh, this is 1, that's 2. It might think wrongly that this is 2 sets of zeros and this is just 1 over here. So if you're going to use the colon, colon trick, you can only do it 1 time per IP address. And could I have done it here instead of here? The answer is yes, you could. However, the iOS is going to go ahead and take the largest groupings of zeros. If you have two sets of 16 bits or more, and it's going to use that one with the colons. Now, case in point, check this out. Let's compare the IPv6 address that we just put in with the shortcuts that are going to show up from the command line. So let's get out of interface configuration mode, and let's do I'm going to do a do because I'm inside of configuration mode. If I want to do a do command there, and I'm going to say, please show me the IPv6 interface of loopback 99, and then I want a pipe to only include the output that involves a line with the word global or includes the word 2001, which happens to be the IP prefix that I used for that network. Why am I doing that? I'll tell you exactly why. There's a whole boatload of output that command otherwise is going to share with you. And I want to focus singularly here on the basics of the IPv6 address in this nugget. So check out what it did. It said, okay, if we compare this address up here that we put in to this one here, it says 2001, that's a direct match. DB8, look at that, it left off the leading 0. Also the alpha characters, A through F, upper or lowercase, it doesn't matter. It knows that F is 15 in decimal. It knows that A is 10. It doesn't care if it's upper or lowercase. Then we have this 0, so I have those 4 zeros represented here, and that's because the iOS said, I'm going to use the double colon coming up. There's 1, 2, 3, 4. There's the double colon, which is representing those two sets of 16 right there. And then I have the 52, the leading zeros are dropped off. And then I have the 1 with the 3 leading zeros dropped off as well. It's also showing me, because of my mask right here of 64, it's also showing me as the first 64 bits and then colon colon. See that colon colon right there? That colon colon means one or more sets of zeros following. So instead I have 1, 2, 3, 4. That must mean there are 4 more groupings of zeros. And because this is the network, that's how we represent networks. We did it with IP version 4, like 192.168.1.0/24. We zero out the host bits when we represent the network. The same thing happens with IPv6. So we could say that R1 is now directly connected to the 2001 DB801234/64 network, and we'd be spot on. Now I have one last piece of homework that I'd like you to do. So as a review, we have the hex table that I'd like you to write out, not just think about it. I want you to actually write it out. I'd like you to configure that IPv6 address with the /64 on some platform. It could be Juniper, it could be Cisco, it could be Windows, it could be Mac if you want to do it that way. It could be Linux, it doesn't really matter. I would like you to configure that one address, because then you will see when you go back and look at it, the shortcut that it gave you by dropping the leading zeros and using the double colon to represent one or more groupings of all zeros together. The last thing I'm going to ask you to do for this nugget homework is I'd like you to reverse engineer this address and put it into binary. Now, Keith, what does that mean again? Well, it means every character is going to represent 4 bits. So you only have to do it 4 bits at a time. So a 2 is going to be 0010. Done. And the 0 is going to be 0000. And the 0 again, 0000. And the 1 is 0001. Now, I can do that pretty quickly because I've been thinking and working with IP and binary and IPv6 for quite a while. The reason I'm asking you to do this is because it's going to reinforce those critical skills. So when you're working with IPv6 addresses, the whole hexadecimal to binary thing will be almost second nature for you. So there's 3 items for homework. Number 1, write out the hex conversion table. Number 2, go ahead and configure the IP address. And number 3, convert this IP address into binary. Let me share with you the network I've been dying to show you now that we understand the basics of an IPv6 address. Here, this network has 3 routers, R1, R2, and R3. They've all got some interfaces and they've got some devices hanging off of them. And here is our network. Now, when I represent this, what does that mean exactly? Well, first of all, it says the 64 says, hey, the first 64 bits of what's being shown, that's the network address space. So if we see /64 on a host address, or if we see it on a network diagram, we'll know that, hey, it's the first 64 bits are network, which leaves the last 64 by default for host addressing. So here we have 2001, DB8. I've got this group of 16 of 6783, and then I have this X right here. Why would I do that? What is X? You can't go that high with hexadecimal. It's 0 through F as in Frank. X is way too high. Well, that X is simply a placeholder to represent in my topology what the subnet is going to be. So for example, that X, that 16 bits, if it's a 12, that's this subnet. The subnet here is 2001 DB8 678323. The one right here is 13. Over here I have subnet 3, subnet 2, subnet 1, referring to that X as a placeholder for those bits. Now, my other question for you is this. If this right here represents the X, how can that be 16 bits? It's only 2 characters. It takes 4 hex characters to represent 16 bits. So how can 12 fit into a spot that should have 4 characters? And the answer is those leading zeros don't have to be represented. So that's really 0012, 0023, 0013, but we don't have to actually write them in because they're the leading zeros. So my variable of X is representing that grouping of bits 49 through 64, the 4th set of 16 bits. In this nugget, we've identified the questions of what is the purpose of IP, and primarily it's for addressing. We've also identified some very common features between IP version 4 and the new IP version 6, and that is they both have two parts. They have a network portion on the left and a host portion on the right, and the mask is the separating line between them. The IPv6 is represented in hexadecimal, and your homework assignment that we've talked about, and I'm reminding you right now about, is number 1, I want you to write out this table right here, the decimal to hex to binary conversion table. Number 2, I want you to configure that IPv6 address that we did in class on one real device. No, a napkin is not a real device. It needs to be a Unix box, a Windows box, a Macintosh, some kind of a router or a switch that can support it. I want you to actually configure it. And when you put it in, and then you use the show command to verify what it is, you'll see that shortening, the shortcut methods in use. Now in production, you and I, as we go forward, we're not going to put in all the extra zeros, the leading zeros, the colon. We're going to take advantage of the shortcuts because they're not only a benefit to the computer, they're also a benefit to us. The last piece of the homework was to take that IPv6 address in hex and convert it into binary to reinforce those very important skills of the hex to binary relationship. I have had a blast. I hope this has been informative for you, and I'd like to thank you for viewing.